Aloha. Welcome to the next lecture of Biology 171. In this lecture, we're going to be taking a look at some of the basic chemistry that underlies all of life function. We're going to be taking a look at chemical bonds, how atoms interact with each other at the most fundamental level that enable the construction of biologically important and, of course, other molecules as well. Exam-like questions for you to think about. The RNA world. The RNA world is a hypothesis. It's probably something that can never be disproven or proven. It's a hypothesis that helps to explain a conundrum. And the conundrum is which came first, the chicken and the egg. Which came first, the chicken or the egg? In this case, the question is which came first, protein or DNA? Protein is the kind of material that makes up all enzymes. It's the kind of material that's necessary for so many different things, not just enzymes, but structural materials. It enables life to happen. The thing with enzymes is for them to be reproduced consistently, they are based on a recipe, and the recipe is DNA. So, to have a protein, or to have an enzyme, you need to have a gene, which is that's what DNA makes up. The recipe is in a gene for that protein. But DNA requires proteins to be able to replicate. They require proteins to be activated. Proteins are necessary to express a gene. So, which came first? How can you have DNA without proteins, and how can you have proteins without DNA? Well, RNA is thought to be the intermediate. The RNA is thought to be the molecule that could have started the whole process. And that's all described in the RNA world, because it turns out that RNA has the capacity to do both the function of protein, in other words, RNA can act like an enzyme, and RNA can also act like a gene. RNA has the potential for encoding information molecule. Okay, what's the difference between the way a fire reproduces and the reproduction seen in living organisms? Well, reproduction in living organisms is based on recipes. And so in order for a living organism to reproduce, it must first reproduce its recipe, in other words, its genome. What's an ecological community? Ecological community is a collection of populations of different species that are all interacting in the same environment. In the last lecture, we ended off with this kind of silly video explaining the structure of an atom. I think it's good to remember it, but of course it's not exactly what an atom looks like. An atom is not a central neighborhood with protons and neutrons around which there's a racetrack of electrons spinning. No. Atoms are more like clouds of electrons that are orbiting a central place where neutrons and protons are found. The electrons associated with an atom are found in different electron shells, and each shell has a capacity. There are a maximum of 2 electrons that can inhabit the first shell of an atom. Now, whether or not a shell is filled or not filled determines whether or not an atom is going to be likely to interact with another atom to form a bond. The more full an electron shell is, the stronger the pull that atom has on the electrons of another atom. We'll see this in just a minute. So the first shell has a maximum capacity of 2 electrons. The next 2 shells, shell 2 and 3, both have a capacity of 8 electrons. We're not going to go any further than that. The atoms that are important for biological life include oxygen, carbon, hydrogen, and nitrogen. That's 96% of the atoms that we use in our bodies, in our life. And then there's a number of other atoms that are more, we don't use as much of them, but that's not to say they're not important. For example, magnesium, 0.1% of our body is made of magnesium, but magnesium is what's called a coenzyme. It enables enzyme function. So without magnesium, for example, DNA polymerase, which is an enzyme responsible for replicating DNA polymerase cannot work without magnesium. Here's a periodic table of elements, and I have highlighted the most significant or the highest levels of atoms that are found in living systems. If we dissect this periodic table, we can see that for each element, for example, carbon shown on the right, there is an atomic number. The atomic number is at the top of the little box. The atomic number describes the number of protons in that atom. The mass number is the number of protons plus the number of neutrons found in a particular atom. And the atomic mass, similar but different, is the average mass number for all of the isotopes of one element. So what do I mean by isotopes? Well, it turns out that there are more than a single flavor of an individual element. For example, carbon. Carbon has two different isotopic states. One called carbon-12, for which there are 6 protons and 6 neutrons found in the atom, and another one that I'm sure you've probably heard of called carbon-14. Carbon-14 has 6 protons and 8 neutrons. Now, if a radioactive element is one where the isotope can decay spontaneously. So isotopes are 2 atoms of an element that differ in the number of neutrons. Radioactive isotopes are those that decay spontaneously. So an example of a radioactive element or a radioactive isotope would be uranium. Uranium-238 will spontaneously decay into plutonium, into thorium. In doing so, gives up an alpha particle, and an alpha particle is a helium particle, a helium atom. Radioactive isotopes are very useful in scientific settings because we can use them and their spontaneous decay to track different biological phenomena. Like on the middle panel, we see the development of expression in a Drosophila embryo. We're using the decay of a radioactive element, probably P32 in this case. The decay exposes an X-ray film so that we know that a particular gene, in this case, is active at a particular time during development. Radioactive decay was also used in all the DNA sequencing that was done probably in the early 80s and, all through the 80s and through to the early 90s. Radioactive decay can also be used to date things. Because we know that there is a particular ratio of one isotope to another, the spontaneous decay of one of those isotopes can indicate the age of a particular piece of organic material. For example, a piece of wood. A piece of wood found in a dig like this one shown in the slide, the pieces of wood are the black horizons. The black horizons tell us something about decaying organic matter. These are probably piles of waste food, or maybe like a midden pile, or could even be a fire. The very dark sooty stuff is probably a fire. Now we can age the fire, or we can age the wood that was used in the fire, because the wood was a living thing. And while it was a living thing, it was exchanging gas with the environment, and so it maintained the same C14 to C12 ratio. As soon as that tree died, it stopped living. It stopped incorporating the carbon dioxide in the atmosphere into sugars. So carbon-14 started to spontaneously decay, and so the ratio of carbon-12 to carbon-14 changes in dead organic matter. And so we can calculate, based on that changing ratio, how long that thing's been dead. That's the basis of carbon-14 dating. The atomic clock, that's the thing that your cell phones check to keep the right time on your cell phone. That's just based on radioactive decay. Here is another video that I would like you to have a look at. It gives you a way to get a handle on the size of an atom. The size of an atom, I think, is very difficult to imagine because it's so small. There's a joke in that video that talks about ground state. Why does a hamburger have a lower energy than a steak? Because it's in the ground state. Now, what the heck is the ground state? This is a science geek joke. The ground state is talking about an energy level that an electron can occupy in an atom. When an electron is excited, this might happen, for example, during photosynthesis, when a photon excites an electron that's in an absorption pigment. That excited electron jumps to a higher electron shell. That's called the excited state. An excited state compared to the ground state, where the electron is in the lower energy shell. Okay, I want to start talking about how individual atoms can interact with each other. All matter in the universe is made of individual atoms that combine and form bonds with each other. The way in which atoms combine, the type of bond, is influenced by their stability, which is determined by the number of electrons they have in their outer shell, the degree to which that outer shell is full. Atoms are more stable when their outer shell is full, and an atom will share electrons with another atom in order to fill their outer shell, if only some of the time. So examples of atoms and the number of electrons that are found in their outer shells would be hydrogen. Hydrogen has one proton and one electron, so the outer shell is half full, compared to helium, which has two protons, two neutrons, and two electrons. So the outer shell of helium, as with the outer shell of neon and argon, these all have complete or filled outer shells. And those three, helium, neon, and argon, are part of a collection of elements in the periodic table that we refer to as stable or noble gases. They are not reactive. They do not form bonds with other atoms. Compared with hydrogen or carbon or sodium, all of which have incomplete outer shells and so react with other atoms. The ways in which atoms can interact with each other are covalent bonds, hydrogen bonds, ionic interactions, van der Waals interactions, and hydrophobic interactions. So covalent bonds and hydrogen bonds, ionic, van der Waals, and hydrophobic interactions all have different strengths. But in the same way that magnesium isn't found in very high quantities, but nevertheless is very, very important in living systems, so also are hydrogen bonds very, very weak compared to covalent bonds. But you certainly couldn't say that hydrogen bonds are less important. Hydrogen bonds are phenomenally important to how life works, how enzymes function, well, the list is a very, very long one. So let's take a look at these individual bonds. This is an aside for the really geeky in the class who want to get down to the heart of stability and bond formation. I'm just going to skip this for right now. So a covalent bond. A covalent bond occurs when two atoms share one or more pairs of electrons. So a classic example of this would be two hydrogen atoms. Remembering that hydrogen has a single electron in its outermost shell. Two hydrogen atoms, therefore, can share their outermost electron, or their only electron, with each other. In this case, the two electrons will orbit both nuclei of both hydrogen atoms. And because the atoms are the same, because they both have the same pull on those electrons, the electrons are going to spend an equal amount of time around both of those nuclei. In other words, the distribution of electrons around both nuclei is going to be even. That's going to come up in just a second. So different atoms can have different numbers of covalent bonds. Hydrogen, because it can only take in one additional electron, can only have one covalent bond. Oxygen, on the other hand, can share two covalent bonds. Phosphorus, for example, can share 5. So covalent bonds come in two different types. A non-polar covalent bond, that's the kind of covalent bond we see with two hydrogen atoms. Non-polar covalent bonds form when the electronegativities of the two atoms are approximately equal. So just an aside on electronegativity. Electronegativity can be thought of as the pull that an atom has on an electron. So the strength at which that atom can pull the electron toward it. If the strength of the electronegativities of two atoms is equal, then the electrons are not going to spend any more time around one of those nuclei than it will around the other nuclei. And so charge-wise, the covalent bond is nonpolar. Now, when two atoms engage in a covalent bond where the electronegativities of the two atoms are quite different, and you can see that at the bottom of the slide with the hydrogen not having a strong electronegativity. So in this case, the electrons are spending a lot more time around the other atom. Okay? We can see this with water. Water has a very uneven pull on the electrons. Oxygen has a much stronger electronegativity than hydrogen. And so in the top right-hand corner of this slide, you see that the electron cloud is bigger around the oxygen than it is around either of the hydrogen nuclei. That means the electrons are spending more time around the oxygen, and as a result of that, oxygen is more often a slightly negative charge because more of the electrons are around the oxygen than around the hydrogens. And as a result, the hydrogens have a small positive charge. So that's called a polar covalent bond because there is polarity of charge across this molecule. Oxygen has a slightly negative, that's what that little funny O with the tail on it, that's actually a lowercase delta. A delta negative around the oxygen means it's partially negative there. And the hydrogens have a delta positive, so a partial positive charge. Now because of this polarity of the charges, individual water molecules can interact with each other using what's called a hydrogen bond. In this case, the partial negative charge of the oxygen of one water molecule is attracted to the partial positive charge of the hydrogen of a different water molecule. That's that dotted line indicating the hydrogen bond between the oxygen of one water molecule and the hydrogen of another water molecule. So a hydrogen bond is the product of polar covalent bonds, or unequal charge distribution. Hydrogen bonds are weak, certainly much weaker than covalent bonds, but they couldn't be more important. Here I'm showing you some examples of how hydrogen bonds hold cellulose together. Individual sugar molecules of cellulose are held together by hydrogen bonds. And that's the difference between cellulose and starch, is the number of hydrogen bonds between the sugar molecules. Hydrogen bonds also hold the two individual nucleic acid strands of a DNA molecule together. So pretty important. Now water has very, very unusual properties. These unusual properties are the result of hydrogen bonds. Water is unlike every other molecule on this planet. Every other molecule on this planet, when it gets colder, it gets smaller. And up to a point, that's true of water as well. But what's very unusual is when water transitions from the liquid state to the solid state. In every other molecule, when that happens, the solid state is smaller. In the case of water, the solid state is bigger. So water gets smaller, 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 and then when it crystallizes, it gets bigger. This is very, very unusual, and it allows life on this planet. So water has a number of very unusual properties. One is that it's polar. The polarity of water enables things to be dissolved in water. I'll show you that in a minute. Water is also sticky with itself. This is very important because it allows things to float on top of water. It allows organisms to live on top of the water. And it allows things like vascular plants to draw water up from the ground to the top of the plant, which could be 300 feet above the ground. And they do that because water is sticky to itself and also to other substance. Another very important quality of water is that when, as I said just recently, when it freezes or turns from a liquid to a solid state, it expands. Now, it's hard to imagine that this would be important in Hawaii, but in fact, life wouldn't be possible in the oceans around Hawaii, anywhere in the tropics, anywhere in the ocean, actually, if water didn't expand when it froze. And here's why. If the frozen state of water was the most compact state, then the weight of the oceans would cause water to become so compacted that all the oceans would freeze. That doesn't happen. In fact, what happens is that when water freezes, it floats on top of the water, and that actually helps to keep the water below the ice a little bit warmer. So the three different states of water, gas on the right, liquid in the center, and solid on the left, are shown. Gaseous state of water is the most expanded state, and that's because the individual water molecules are not attached to each other by hydrogen bonds. The volume is compressed when water goes from a gaseous state to a liquid state, because in the liquid state, the water molecules, some of the water molecules are attached to each other by hydrogen bonds. Now, when the movement of individual water molecules slows so much that more hydrogen bonds can form, a crystal lattice is formed, and that's why the solid state expands. It takes up more room to accommodate that crystal lattice. Another very important feature of water is that it has a high specific heat. In other words, it takes a lot of energy to increase the temperature or decrease the temperature of water. That's what makes water such a good insulator. It makes water a very moderating body. If you live in a city that's near a very large body of water, the environment around that city tends to be more moderate, not as extreme temperatures. That's why it can be much, much hotter in the middle of the continent and the northern parts of the continent. For example, where my parents live in eastern Canada, much hotter in the summer than it is here in Hawaii, because their temperature is not moderated by a big body of water. There's a lake there, but it's not big enough to moderate the temperature. Sweating. This is an important thing. It's going to show up on an exam for sure, as is hydrogen bonding between water molecules, guaranteed to be on the exam. How does sweating work? Well, it turns out that sweating works not because cold water is put on the surface of your skin. No. Of course, the sweat, the water that your body is putting on the surface of your skin, is body temperature. It came from inside your body. When you put that water on the outside of your body, when you sweat, the heat from your body causes that water to vibrate. It causes the individual water molecules inside the water to move more quickly. That heat energy is being transferred into molecular kinetic energy, and the individual water molecules moving more causes the hydrogen bonds to break. and that enables the sweat on the surface of your skin to evaporate. So it's actually the evaporation of the water that's cooling you off. That's why it works to use a fan. If you're in a hot room where there's not a lot of air movement, using a fan causes the buildup of high humidity air next to your skin because the wind isn't moving it away. The high humidity reduces the rate at which you can evaporate because the air is already saturated with water next to your skin. When you use a fan, you're blowing that high humidity air away from your skin. That allows you to evaporate more sweat. That cools you off more. Doesn't work on a really humid day. Why? Because all of the air is already saturated with water. So that greatly reduces the ability for the sweat on your skin to evaporate. And so it's not taking heat energy from your body. Just an aside, if you've ever tried ice skating works because the blade of the skate actually in cross section looks like the top right hand side of the slide. Two very, very fine edges. And the two very fine edges concentrate your body weight on the ice. And in compressing your body weight to such a fine area, that causes the ice to be compressed to a liquid state. So when you're ice skating, you're actually floating on top of liquid water. The cohesion of water enables, as I was saying earlier, things to live on top of the water, like this water strider. Cohesion also enables water to be drawn up from the soil because the water molecules stick to each other, and as the water transpires out of the top of the tree, the vacuum that's created at the top draws the water up from the roots. And a thought to end this lecture on.